Alright, so I wanted to continue a little bit on the SSH kind of way of thinking that we talked about on Friday. So we talked very briefly about SCP, but I wanted to talk a little bit more about how we can actually use it efficiently to transfer files. So by default, SCP actually has kind of functionality to copy entire directories and things like that, and I'll show you that in a second here. But what might be a more efficient way of doing it would be to archive that data first and then copy it over. And then the second topic I wanted to talk about today is process management. Talked a little bit about it on Friday with PS, so you could see all of your processes, see the tree, kind of see how SSH spawned processes in response to user input. So I wanted to talk a little bit about that. So I have our two VMs here that I'm going to be looking at. I'm just SSH'd into them from my desktop here. Another random interesting command that I want to show here is hostname-i. So if you want to get just the IP address of your box, really nice and easy like that, you can just say hostname-i. Normally you'd have to say ifconfig, and then parse through all of this data. But with hostname-i, you can just instantly get your IP address, which when we get into doing scripting stuff with bash and whatnot, that turns out to be really nice. So let's look at this. Let's say we have, don't know why that's there, I'll delete that file. Let's go ahead and make a directory. And I'll just copy some random files in there. So I'm just going to copy some programs. So I'll copy ID, I'll copy, let's say ls. I can't do ls actually. Let's do grep, that's a good one. It's not in user bin, it's probably in bin. Cool. So I got just some two programs there. So one way I could get this directory right here over to this box is say scp-r for recursive. So we'll take the directory and it'll take everything underneath it and it will copy it over to what my target is. So again, scp is just like cp, it has the standard source and then destination syntax. So I'd say dir, and then I'd say DSU at 192.168.253.55, and then I'd use this colon dot to put it in the home directory or the current directory. So we have this dir right here. And that worked pretty easily. Pretty straightforward. Now, if I was to find a bunch more files and make this artificially bigger, that scpr would actually take a little bit of time because it would have to, like, behind the scenes, it would do something like open up a new session for each of these individual items and transfer them over and over and over, one by one, and that kind of gets painful and tiresome after a while. So what we can do, and what's usually the way that we would do something like this, is create an archive before we would copy it over. So just before we do this, let's see what happens if we left off this -r. It would say dir not a regular file. So it wouldn't be able to copy that. It would actually, so when we're doing the -r, it actually goes down, it looks through everything, it finds all the files that are part of that folder, and it copies those files over. So anyway, what we probably actually want to do is create an archive. So on a Unix system, not clar, clear, what we use to create archives, generally speaking, is the tar command. So hopefully you remember that from operating environments. What we say is cf, so we say C to create a tar archive, we say F to specify the name of the tar archive, or the name of the tar archive, and we'll just say dir.tar, and then we'll say dir. And that will take the contents of dir and it will put them inside of this archive. So to look and see what we have in that archive, we can say tar tf and then say dir.tar. And it'll actually show us the contents of that directory. So we can just scp dir.tar and then DSU 192.168.253.55. Go over here. We just say tar xf, so extract, and then the file name dir.tar. And there we go, we got it. So that's the basic usage of tar. The other way we can use tar is to actually add compression in at the same time. So when we're talking about compression, it's usually useful to actually give a little demonstration first. So let's just take this. Let's find our SSH config. We'll drop it right here and we'll look at it. So it's just a configuration file, obviously. So to compress that file, we could just say gzip sshd config. And what that will do is it will overwrite the existing file with a compressed file. Now to undo that, you could say gunzip. So it's basically g uncompress sshd config. Sometimes it doesn't exist. The other way you could do it is gzip d. So it's gzip decompress sshd config gz, and that would just replace it. So let's actually look at that really quick. Let's say lh, so that will list the extended view and it will show it in human readable form. So let's look at that. SSHD config is 2.5 kilobytes by default, and that's of course off the screen. 2.5 kilobytes by default, but if we gzip it and then we look at it again, now it's only 1.2. So this is a text file. It lends itself very well to being compressed easily. I won't get into all the compression stuff. Just know that gzip is pretty good and it's pretty cool, and it's actually really interesting if you get into it. But when we're copying files over the network, odds are we have more processing power on our local machine in relation to network capability. So it's really nice to compress things before you send them over the network, because you just basically get things for free. So we have this dir.tar ls lh. So that's 250K right now. To actually figure out what the size of all the files in dir are, you'd say du for disk usage. You'd say 8 or s summary, and then dir. And it looks like, if I have this done right, there is 252 kilobytes of data in dir. So, and then when we made it into just a plain tar format, so that's no compression, it's just putting all those files basically in one file. We're at 250K, but let's see what happens when we cfz. So when we say C, we mean create. When we say Z, we mean use gzip compression. And when we say F, let me just clear this. When we say F, we specify the file name on the command line. So we'll just say dir.tar.gz. So normally you would say tar and then whatever compression you're using, and then we'd say dir. Let's look at this again. LH. So we can see we actually pretty much halved the size of that. And I could go through and I could give a lot bigger examples, but this is pretty much good enough for this basic thing. So let's say I need to copy a huge directory of thousands of files of a number of some arbitrary number of size apiece. We definitely want to compress that first into one tar archive. So again, to copy that over, we just say scp. I'll just go up in my history and find it. Scp dir.tar.gz. Go over here, see you have a new file created in the home directory. Another thing to note is, let's say we wanted to give that file a different name when we're copying it, so we didn't want it to be dir.tar.gz anymore. We wanted it to be archive.tar.gz. We could just give it that name right on the command line, run that, and we see we have this archive.tar.gz. So let's just remove a couple things here. dir.tar. Let's remove all of those. So tar xf, so extract file archive tar.gz. And there we got our dir directory with everything that we had in it originally. So one thing to note is I didn't actually put a Z in here anywhere. So it actually used to be the case that you had to manually specify what type of compression that your archive was using, but nowadays tar can just detect that and figure out what's going on. So if you use the file command here, remember that file kind of tells us what type of file something is, or it doesn't kind of, it does. It can detect that it's gzip compressed data right inside there. So automatically it would know. So one of the ways that the file might figure out what a file contains is by looking at its file extension. So to verify that it actually doesn't do that, we could move it to just archive and just remove the file extension. And then we could say file again, archive. And file would still be able to determine that this was in fact gzip compressed data because of these magic numbers that are a part of every file in most systems, including Unix. So I could, let's see if I can do this. It's not particularly important, and of course my terminal is too small to actually see it. Basically, when you have a binary, so there's a binary file, and then there's a text file. So text file is something just like, I don't have it over here anymore. Where'd my SSH config go? CP. So text file just has raw text in it. You can read it very easily. So a binary file is something that's not really meant for you to specifically read. It's data. And in binary files, we have these things called magic numbers at the very beginning of the file, which indicate that that file is actually of a certain type. So an executable might have a certain magic number, and a tar archive might have a certain magic number, and a gzip might have a certain magic number. So magic number in programming. Nope, that's not what I want. Or maybe is it? Maybe it is. But yeah, so here's a bunch of different like binary file formats. So magic numbers and files, and it's the Wikipedia page on this. But you can see that there's kind of just these beginning hexadecimal in this case, hexadecimal representation in the headers of files, which indicate what type of file that actually is. So it can be parsed by the appropriate software. So it's kind of interesting, just tangential, not really that important. But so let's see here, anything else to talk about? So yeah, that's just the basics of compression, I guess. Things that I hope you'd gotten into in operating environments a little bit, but I wanted to show you how you could kind of combine that with SSH and SCP to copy things over, which if you want to do a demo, I mean, you could do something like copy all of your root directory or something recursively, or copy the entire bin directory recursively, which is going to amount to hopefully a few megabytes or something like that. And you can see that it's much faster, definitely, to add those things to an archive first. So let's see what we have next here. Just talked about tar, talked about SCP. Okay, so here's the big thing that I wanted to talk about today, was process management. So we talked about this before. We talked about PS. By default, when you run PS without any arguments, it will just show you what you're running currently. So in order to make this demo a little bit better, I'm going to SSH over to the other machine so we can have multiple things running at once. So I could run PS, and it will show my current shell and the current processes that I'm running, but it doesn't show the shell over here. Same this way. So let's say I have nano open or something, and I run PS. It will only show me the processes in my current session. Now to show, I think it's pretty sure it's A. PSA would show me all of the processes that my user is currently running that are foreground processes. We're going to talk about foreground processes and background processes in a minute here. PSA, if I do PSA-U, it would show both my processes and my processes that are running in the background. And then if I say X, it will show me processes by all users that are running foreground and running in the background. Unfortunately, font is going to be annoying there. So let's look at that a little bit more. Remember, we have this PSOXF, which can show me the tree, which is really cool. So my SSH service spawns additional processes for each user that's connected. Remember that? Remember that to do something fun like killing this user, you could just find their process here. I don't know exactly which one it is. Let's run nano again. You can see we have nano in this one right here in this process tree. So I could find their PID and I could just do kill that and it would disconnect them. And they get disconnected. So it's just kind of interesting. So what's more interesting in my mind is job control and all of that kind of stuff. So you've probably experienced this in 150. You probably hit Control Z at some point and backgrounded something. So let's say you have nano open and you're just looking at this. I don't have my nano ID RSA.pub. And you hit Control Z. So it'll say stopped and all of that. So you can say jobs, to see the jobs that are running in the background, you can say FG, and it will foreground that job again. Or you can say BG, and it will allow that program to run in the background. So let's look at this then. So we'll say PSAF. So we have our PSAF right here. This is us. This is the other terminal. So you have this background process. Let's say you go and exit your terminal. You'd say Control D. It would say there's stop jobs. But let's say you just chose to ignore that and didn't really care. So when you log out, I'm back on my other Ubuntu box right here. When you log out, that nano is just killed. It's just in the background. And we're going to look at why that happens and how exactly that happens. So, in order to do this, it's kind of useful to know a little bit about different signals that we can send to processes. So, let's SSH back over here again, and let's say nano ID RSA.pub. And since it didn't close cleanly, it's going to be annoying. Sure. Yep. Okay. So PSAF. Let's say we wanted to kill just this nano process. Let's say it had become unresponsive, wasn't responding to user input or something like that. We could say, we could copy that PID, we could say kill, and then that. And what that does is it sends, I believe, sighup by default, or it might send sigterm. So, not man signal is what we want to look at. So on Linux, there's a number of different signals that we can send to processes. So all of these signals can be hooked up to different things, essentially, and each process can generally do different things. Let me find the actual list of signals here. So this is what we're really looking at here. Is this table right here. So the important ones to look at are sighup. So hang-up detected on controlling terminal. So when the terminal that owns a particular process closes, it will send this sighup to any child processes of that terminal. It's kind of important. Sigint is Control C. So if you send Control C, it will send this sigint. There's a number of other ones here, but the other important one is sigkill. So with sighup and sigint, you can actually catch those signals, process them, and your program will continue. But with sigkill, your program will immediately halt, will do no further processing, and will stop instantly. So let's do a little bit of demonstration with that. We can specify which signal we want to do on the command line. We could say kill, and we could say the number of the signal. So we could say 9 for sigkill, or we could say kill. Let's start out with hup, or let's say term. So term would be Control C. So we'd say, let's just do nano again. Yep. And then PSAF. So we could just say kill term, not process. And it still says sighup or sigterm. So I guess in Nano, what they do is if you receive either of these signals, it's processed as just exiting. But if we look at Vim, RDA state.pub, edit anyway. So normally when we control C in Vim, it doesn't actually let us exit, of course. The age-old problem that people have with Vim. So let's try and kill that the same way we did over here. So we send term to it, which would be control no, it'd be int. Sig int would be control C. And you can see it doesn't do anything. So in the case of Vim, it's actually catching that signal and just kind of ignoring it. And it actually does do something. It does tell us that we can type :Q to quit. But let's see what happens when we send term. It does actually stop. One more, let's look at hop. Process doesn't exist anymore. It will also stop. But finally, let's look at the final one. Let's look at kill. PSAF. Now what's different about that is every other time we've terminated Vim, it actually cleaned itself up. It actually exited cleanly. It would have said caught deadly signal, and then it would have exited. But with the sig9, sigkill, it doesn't do any further processing. It doesn't clean up the terminal at all. It just immediately stops. So in this case, we'd have to do something like clear or reset to fix the terminal and clear all of that output. So to look at this a little bit more, we can actually write a nice little bash script which will allow us to catch these signals and process them. In this case, we're just going to indicate when we see them. So we'll just say signal.sh. Got our little shebang there to indicate that we want to run this as a bash script. It's this way, bin bash. And then let's see what we have. I have this example over here. So what we can use is we can write a function. Let's just catch, right now, let's catch hup. We'll call it catch hup. And what that will do is it will just say echo hup, and that's all it will say. So in order to actually direct our signal at that function, what we would say is signal, we'd say what we want to call, catch hup, and then we'd say sig hup. I think this is the way it worked. Yep. No, signal is the way you do it in C. There's a trap function here. And then what we'll do is we'll just say sleep for like 1,000 or something like that. So remember, got to give that execution bit for it to work. So you do that, signal sh. PSAF, we can see we're running right there. And let's see what happens when we send hup now. HUP. And it didn't do anything, that's interesting. Let's see what happens when we don't attach that signal handler. So the one thing I'm kind of concerned about right here is sleep might not be giving us what we want. So kill hup, and there we see hang up and it just exited. So this is kind of interesting. It's really, in my mind, weird that happened. Let's do something like this. Let's do 10 seconds. I'll do 15. I'm sorry, I'm getting up on tangents here as usual. PSAF, kill sig hop, and then I'll wait for a second here to see what happens. So what I'm thinking is happening, yeah, okay, that's what's happening. So when we're doing sleep, it actually registers that signal, but it won't process it until this particular line is done, which is kind of interesting, I guess. If I did, let's say, I'll just netcat, listen on port, 8888, I think that should allow it to work right away, just for random reasons. No, okay, so signal is only processed after that particular line is done executing. But it's kind of interesting regardless. So let's say we wanted to we'll come back to this in a little bit, all of this kind of stuff. Basically what you can do with all of these things is either process these signals or just completely disregard them. So that's kind of interesting, I think. But let's go all the way back to the beginning and talk about what happens when something's running, it gets backgrounded, and then you close your terminal. So I'll still do this signal at SH even though the demonstration doesn't matter anymore. I deleted the netcat. So I'll run that, I'll background it, and it'll BG. So it's running in the background now. So PSAF. So there's our stuff. And then let's say we disconnect. It will just say connection closed. But the interesting thing that's going to happen now, I hope, is AF, PSAUX, grep for signal, is the signal is actually still running in the background. So it's still running and everything. If I look at my netstat LTPN, we can see that there's still something listening on 8888 from that netcat that we spawned earlier. Fortunately, it's down at the bottom of the screen again, and it's actually still running in the background, which is kind of interesting, I guess. And the whole reason why that's happening is because we caught that signal hup. So again, when we close our terminal, that sig hup will be sent to all child processes, and they will be killed by default if they didn't define any signal handler. So even though that signal handler hasn't actually been processed in that signal.sh, it basically is waiting to process it. It didn't take the default action to kill, and is actually still running. So let's expand this a little bit. What happens to a process when its parent terminal dies, but it doesn't do anything with hup? So it actually becomes zombified. So remember how by default we had this SSH, we had each SSH session, and then we had just a log of who's running everything. There's this hierarchy of processes, but now we can see our process down here does not belong to this hierarchy of processes anymore. It's still running in the background, but instead of being owned by anybody, it's just kind of running off in the background. You can't actually see it down there. It's down there, I promise. We'll say tail, and we'll only see those final lines. So it's just running off in the background there. So the only way to manage that at all would be to use a service manager kind of thing, like systemd, to keep track of all of those different background things. But let's say we wanted to just get rid of it. We could just say kill 32317, and then it still happened to be there. So need to kill a few more things. and we're getting closer. So it's tricky to kill those background processes. The signals don't go since that hierarchy was destroyed by ignoring SIG-HUP. You might have to kill the entire tree manually, which is just super annoying. But so the other interesting thing that you could do is I'll go back to this signal this signal script really quick here. And let's catch something different. Let's catch int. So hopefully int will be a little bit more interesting. Interesting, that's funny. Int, sig, int. So let's see what happens by default when we do this. Signal.sh, psaf. You can see we got it right there. So let's just send sig int, which remember is Control C. Actually, I can do it right over here. I can just send Control C. I just died. Oh yeah, so that's the default behavior, is it would just die. It would send that sig int to whatever process is currently running in the bash script, and then it would exit. So if I actually turn that trap on, and I need to change my function name here. And I ran this again. Now when I hit Control C, it will still do that, which is dumb. Okay, so the behavior in bash is a little bit different than in C, I guess. Normally, if you did this in C, if you did this in a program like Vim, what would happen is you just kind of discard int or sig int. And you'd have the behavior like in Vim, where when you hit Control C, it doesn't actually do anything. So I guess I've kind of glossed over some of the nuances in bash, so I'll have to apologize for that and not really knowing what's going on. So since I did this netcat, that'll be the final thing I'll try and explain today. So netcat's just a little Unix utility for connecting on ports, listening on ports. So to do this demonstration, I'll go back to my regular Ubuntu box here. So I'm on Ubuntu here. I'm on Ubuntu 2 over here. So we could say NC and then LP. So listen on port, and I'll just say 8888. On this box, I'll say NC, and I'll say my destination address, so 192.168.253.54, and I'll say the destination port, 53, not 63, and I could just say ASDF, and we can see we have data that flows this way. If I wanted to send data this way, I could type from here, and it would send it over there. So it's just a really nice Unix utility for establishing network sockets. You could connect to things like HTTP servers and get raw data from them if you wanted to do something like that. So I could say NC Google, I'll say dsu.edu port 80. I could manually write myself an HTTP request, and it would send me that raw text data back in response. So netcat's kind of just a fun little utility. Let's say you wanted to send this file over the network, but all you had was netcat and you had nothing else. What you could do is cat sshd config, and you could say nc. Let's do this. So we'll say hostname, figure out our IP address, get that, and we'll say nclp8888. Connect to that IP on this port, and it will send that over raw TCP, no encryption, nothing like that, and it'll get here. So that just printed out to the terminal. Let's say you wanted to do something like redirect it to a file, sshd config. You could just redirect standard output there. And now we have this nice new sshd config file that we transported over netcat. So sometimes it's kind of nice to use that in bash scripts to make things nice and such. Oh, final thing that I was going to do. So hopefully you're familiar with the top command. So it shows you basic information about CPU memory usage, a bunch of data that's actually kind of hard to interpret. I don't really ever touch top very much. I like another utility called htop. So to install that, you could say sudo apt install htop. htop. And now we can actually see some really, really cool information. This view is just superior in every single way to top, and I personally have htop installed on pretty much all of my systems. So you have this nice little graph of CPU usage up here. You have memory used, so I believe this is memory used, this is system buffers, and this is cached right here for yellow. It doesn't really matter, but there's that. But what's really cool about this is you could do something like put it in tree view right away. So you can actually have tree view in real time, and you can scroll through it, which is super nice. You can search, and just ridiculously good features. Let's say I wanted to search for bash. I found my process right there. So I definitely recommend, if you are going to get big into doing kind of Unix, Linux system administration stuff, definitely run htop because it's just superior in every single way. So yeah, that's all I had for that. I think that's all I wanted to cover today. I had another topic, but I don't think I'll have time for it. So that's all I got for you. Sorry my demonstration didn't really work out that well. I might try and do a C demonstration next time around that's a little bit more well, not understandable. It's going to be even less understandable, but perhaps better. So I'll also try and post a Lab 3 today dealing with some SSH stuff that we talked about on Friday, and maybe dealing with a couple things here we talked about today. That's all I have for you. So if you have any questions, stick around. We'll talk about it. But yeah, that's it.